The Levenshtein algorithm is an iterative algorithm, and in segment 2 of this lecture, I showed you what justifies this iterative algorithm or this loop algorithm, that is to say the loop invariant. But now we're going to take a different perspective. So welcome to segment 3 of this lecture on distances, invariance, and recursion. Now, there's a different way of looking at this algorithm, which is to say, well, consider the distance between a certain string S and a certain string T. So that's the general view of the Levenshtein algorithm. Let's add two arguments, which are I and J. And so what this actually is going to return is the added distance, or the Levenshtein distance, from the prefix from 1 to I of the source string. I'm assuming that characters are numbered from 1 to the substring, prefix substring 1 to J of the target. How do we do this? Now, let's take the viewpoint of functional programming. Functional programming is a whole mode of programming which is quite old. It goes back to the design of Lisp, the Lisp programming language in 1959 by John McCarthy, but it became a fashion a few years ago again with the emergence of new functional programming languages like Scheme, which is a modern version of Lisp, or OCaml, or Haskell. And the general idea of functional programming is that we try to remove the imperative nature of programming and go back to the stateless nature of mathematics. What does this mean? In mathematics, there's no notion of change, which exists in programming. In programming, we're dealing with the finite memory of a computer, so we have, again and again, to use the same memory cells to write new values and, of course, to read these values. So we change the values of these cells represented in our programs by variables. A variable in programming deserves its name. It's something that changes over the execution of the program. To be more precise, it changes its value. The variable doesn't change, but the value of the variable changes over the execution of the program. If you think about mathematics, which also has this notion of variable, it's something quite different because there's no real notion of change. If I take the square root of x, where x has value 2, nothing changes. 2 doesn't change, x doesn't change, square root of 2 that doesn't change. We're just describing relations between mathematical objects like 2, a square root, and other such objects which existed before and will still exist afterwards. We're just describing connections between those elements, but everything was there and will be there for eternity. So this is a main principal difference between the world of mathematics and the world of programming. The world of programming is imperative or stateful, meaning that it has a notion of state, a set of variables whose values can change. Mathematics is stateless. So functional programming tries to get back to the simplicity and ease of reasoning of mathematics by rejecting the notion of state and the notion of change. Now, there are functional programming languages, as I said, but you can write functional programming programs in I4 just as much as in any other language. Actually, I4 has very strong support for functional programming constructs, in particular high-level functionals through agents that maybe I will cover in another lecture. But here we can see it in a very simple way with this variant of the Levenshtein algorithm implementation, which, as you can see, has no assignment except for the assignment to result. Of course, we do need to return a value, but it's single assignment. It's not like result changes values over the execution. It's just assign a value once, and this value is the value of an expression, an if then else if expression. It's not a conditional instruction, it's a conditional expression. So what does it say? It says, okay, we're trying to compute the added distance from S of 1 to I to S of to T of 1 to J, the corresponding prefixes. So if the source string is empty, look at this. Okay, we have a precondition. This is of course Eiffel specific. Functional programming languages typically do not have these so-called design by contract constructs, which actually are very important, and I can hardly understand why you can program without them, functional programming or not functional programming. So here we're stating the conditions, right? We're stating that I is between 0 and the count, the length of S, and J, same thing, is between 0 and the length of the target string T. So first case, I is equal 0. The source string is empty. So, well, the minimum way to obtain T from an empty string is to have a sequence of J insertions. This is mathematically clear. If J is 0, that is to say, if the target string is empty, then the minimum way of obtaining the target from the empty target from the source is to delete all the characters of the source. So it's going to be I operations. Else, if S of I is equal to T of J, so in this case, we know that I is not equal to 0 and J is not equal to 0. So we can talk about S of I and T of J, thanks to the precondition, which says that they are within the bounds of the respective strings. So we know that if we were able to get in I minus 1, in a certain number of transformations from the I minus 1, J minus 1 prefixes, respectively, then since the letters at positions I and J are the same, we can obtain the extended string transformations by doing no more transformations. Okay, so in this case, this is obviously the minimum that we can get. And now in the general case in which I is not equal to 0, J is not equal to 0, and the letters are different, then we can consider the substrings. I say, of course, it's the same reasoning that we did for the iterative version. We can obtain the new strings by insertion, deletion, or substitution. And given the minimum of the 3 distances between those respective substrings, we are going to have one more of this minimum, depending on whether we get the minimum through an insertion, the first case, a deletion, the second case, or a substitution, the third case. I call them L, U, and UL for left, upper, and upper left, in reference, of course, to what we had in the iterative version, but here there is no matrix. It's just a mathematical definition, a mathematical proof, if you like, of the Levenshtein method for getting from edit distances between substrings to edit distances between the entire strings. By the way, if we really want the Levenshtein distance, we are going to have to do something like this. We are going to have to define a function distance between 2 strings with only 2 arguments in this case, which uses the lengths of the respective source and target string as a third and fourth argument. When you do functional programming, it's very often like this, that you have to define auxiliary functions with more arguments. So you can see this as a mathematical definition. You can also see it as a program. You can actually write this in Eiffel. It's going to compute. I haven't done it, but you're welcome to take my example program and change it so as to replace the formula for computing the distance by this one. Is going to give you the same result as the iterative version. This was the iterative version. And of course, they have a kind of kindred look. They really, it's clear that they are related. How are they related? Well, this is what we're going to see next. But the problem is that if I implement this functional programming algorithm, it's going to be hopelessly inefficient. So for small, modern computers are fast. So if you use small strings, it's still going to come back with the results relatively quickly. But if you use bigger strings, you're soon going to get into a combinatorial explosion and very long execution times. Why? Well, if you look at it, if you look at this code, you see that it's going to recompute the same distances between the same substrings of the source and the target again and again and again. So at this point, this is an algorithm that is perhaps very elegant for people in particular who like the elegance of mathematics and of functional programming, you know, who like to have stateless, non-imperative programs, but it's not something that you would ever want to program for any significant application because it is absolutely hopelessly inefficient. So can we make it better? Can we keep this simplicity and have a faster execution? And more generally, what is the actual connection between those two variants that we have? The iterative version with its loop invariant and the mathematical version, a functional programming version with its mathematical definition. And of course, the reasoning which led us to this mathematical definition is tantalizingly close to the reasoning that we had to explain the invariant in the iterative version. So what exactly is the connection? That is what we are going to see in the third segment of this lecture, where we're going to go in depth into the connection between the two versions and moving beyond Levenshtein to a whole class of algorithms for which these ideas are applicable.